Hi everyone, today we will be doing the problem fire. This is from the JOI final round 2020. In this problem, we are first given n districts number from 1 to n. Now we are told that a fire starts in each district at time equal to 0. Now we are given how the fire spreads. Essentially, let's say if the strength of the fire at a particular cell C was, let's say, 5, and at the cell C plus 1 was, let's say, lesser than 5, so it can be, let's say, 3, then after 1 second, or rather after 1 unit of time, the strength of fire at C plus 1 also becomes 5. That is, whatever the strength of the fire was at the previous cell. So that is why it's given here like S of I of t, which basically means that S of I is the strength of the fire at the ith place at time t. It becomes max of strength of the fire at the I minus 1th place, basically the previous place at time t minus 1, and at the strength of the fire at the current position in the previous time. So after every 1 unit of time passes, we update all of our SI values using this formula. Now in queries we are given a triplet of numbers T, L and R. So for the jth query we have to answer that at the time Tj, what is the sum of strengths of the fire from Lj to Rj. Now the number of queries and the number of stations are both 2e5. There are some subtasks, but we will directly attempt the solution for the final subtask. So let's get a feel for what the problem means in a pictorial way. So again I will be drawing the strength of the fires as a line on the xy plane. So let's say the strength of the fire at point 1 was something like this. So this is, let's say, 10. At point 2 it was, let's say, 2. At point 3 it was, let's say, 8. At point 4 it was, let's say, 14. And we can keep drawing it like these. Now this is the version for t equal to 0. Now what happens when we move on to t equal to 1? Now we are at t equal to 1. Now what has happened is the strength of 2 effectively becomes the strength of 1. So it becomes like this. Well, now what is the strength of 3? Well, strength of 3 is effectively the max of this and this. So it just remains what it was. Strength of 4 is max of this and this. So again it remains what it was. Strength of 5 is the max of this and this. So it increases by this much. Now for 6, 7, 8 nothing changes because they were greater than the previous values. So it remains like this. Now let's say we move another iteration. Now we are at iteration 2. Now remember that this was the scenario in our previous case. Now here what will happen is 3 becomes the same as these values, so it also becomes 10. This becomes the same as all the previous values, and these don't change because in the previous iteration this was still greater than this one and the last one was also greater. Let me draw it in a different way. Let's say this was a block and then these were the other blocks. So what happens is after, let's say, the first iteration, this part becomes the same height, this part becomes the same height, and this part becomes the same height. Then after the next iteration, till here it becomes same height, till here it becomes same height, till here it becomes same height. Then let's move on to the next iteration. It becomes the same height all the way up to here. It becomes the same height all the way up to here, and it becomes the same height all the way up to here. So now what has happened? We essentially have 3 blocks of these heights. This block has essentially stopped. I mean, next time this person won't be updated, obviously. So this person won't be updated next time. So the expansion, so I'll call this as an expansion. So the expansion of this block ends when it first meets another block which is greater than its own height or greater than equal to. So this is kind of the expansion phase. So I'll call it as phase 1. Now the expansion for this block is obviously ended, because I mean at the end you can just assume that a wall of infinite length exists, because there is nothing here to extend to. For this particular set of blocks, so that is basically the expansion that started from this position. This expansion will continue to happen till it reaches the final layer. That, like, this is the end point, right? So this is the array end point. Till it reaches the end point, it will keep on extending itself. Now let's try to dissect our situation a bit more. For now, it seems hard to keep track of when, or rather how I can calculate a value from A to B at a time t, because at every time the values keep on changing, and at every time it's not like only one value will get changed, several values might get changed. Now how can we make some more observations? One way to attempt to calculate these values is if we can keep track of what value is in a particular location at a certain time t. So this seems very hard to do, because again at every iteration multiple values might change, and we cannot really know for sure how many values are changing, and the number of times that the values changes can be overall quadratic, because let's say we consider a set of values like this. So this value will override these values n times, this value will override these values n minus 1 times, and so on. So overall there will be n squared changes, and it seems very awkward to try to maintain all these changes in an array. Maybe it could be done. If it can be, do mention in the comments. A much better way here would be if for every value, rather if for every I, we know how many occurrences of AI are there presently. So what does this mean? Well, notice how the strength of the fire kind of spreads. It initially starts with this kind of a situation, then it becomes this, then it becomes this. So what happens here is it's almost like this value is overriding this value, and then it's overriding this value, and so on. So I am saying that the number of occurrences of ARR of 1 is increasing. That is why I call this as an expansion phase. So that is why I called it as an expansion. A value ARR of I will keep on increasing till it hits a value that is at least as large as it. So some value here. So in an expansion phase, let's say we are at time t, the number of occurrences for this particular I, let's say ARR of I, it is just ARR of I, or rather it is exactly min of t comma What is the maximum number of time this can increase? Let's say there are 1, 2, 3, 4, 5, 6, 7, 8. So it can increase 7 times. So it's basically min of t comma 7 plus 1 because there was an initial occurrence here. So this is the number of time the ith value will occur at time t as long as it is in the expansion phase. But notice how we are kind of deleting certain elements here. So there was maybe an element like this here, there was maybe an element like this here. These we are deleting, and once an element gets deleted, it seems from here that we don't really want to count it anymore. So there is another phase that an element may enter. It is the delete phase, rather deleted phase. I'll call this as phase 4 for now. There can be some other cases as well. Notice how here I am not looking at the static picture, I am kind of looking how the strength of the fires kind of evolves over time. So another case can be there is a value like this and it can increase, let's say, till this point, because after this, let's say there is a bigger value, something like this, and before this there was a value like this. So from our previous calculations we can try to say that okay, this, and let's say we are calculating for time t equal to 6, we might say that okay, the number of occurrences for this particular value is, let's say, min of t comma 1 2 3, so t comma 3, rather not 3, I mean something large, let's say 11. I am not sure how many values there are exactly here, but anyway, so let's call this 11 into, so this is the number of occurrence of this particular I, and the value here is error of I, and let's say plus, we want to account for this, how many times it has increased. Well, again, let's say it has increased ARR of j, so this value is, let's say, j, this value is, let's say, I, into min of t comma, let's say there were 7 elements here or 8 elements here, right? And then we have to somehow account for the fact that these elements all got destroyed, or rather deleted, and are in phase 4, but let's not worry about that now. Even for this data, this is incomplete. Why? Notice that at, let's say, time equal to 6, this value has indeed propagated 6 times. So this ARR of j value, so it might seem that okay, why not just put 6 into ARR of j, but in actuality the values from here have deleted some of the occurrences of the ARR of j. How can we characterize this phase? Here it is essentially after every unit of time, jth element is expanding to the right, but it is also decaying from the left. So the overall number of occurrences kind of remain the same. So this is the number of occurrences, let's say t equal to 7, at t equal to 8, this is the scenario. So the number of occurrences is this region, which is exactly the same as the number of occurrences in the previous region. So it is not expanding, nor is it decaying. So a state of decaying would have been something like you are already, you have already like reached this maximum potential that you could have expanded to, and for some time nothing happens, and then there is a larger range here which catches up to you and starts deleting your occurrences till it hits the wall, and when it hits the wall at the right, you are completely deleted, so you enter phase 4. So I call this stable state as stage, let's say, so this is like a stable state, I call this phase 2a. Why 2a? Well, After, so this is not the only stable state. Another possibility of a stable state is something like when there's a large wall here, and then you have this value, and then far, and everything here is smaller till there's a very large value here again, and there are, let's say, three values. So after the third iteration, this value would have extended till here, right? This value would have extended till here. After the fourth operation, it comes here. After the fourth operation, it hits the wall. Now it hits a stable state. Now the stable state characteristic here is that it is neither expanding nor is it decaying. So in this scenario, this case was, it was both expanding and it was decaying. Here the scenario, it is neither expanding nor is it decaying, right? So it is kind of what I call phase 2b. So this is another kind of a stable state. And finally, from this 2b, it will finally enter a state of decay, just decay. So I'll write it below here. Yeah, so this is phase 3. So my order got a bit messed up, but hopefully that is okay. So what happens here is that after a certain amount of time, this range, let me draw it in red. So this range finally catches up and it starts removing stuff from here, right? So it enters a phase of decay, and then finally when this red hits the right barrier, you enter a phase of deleted. So that is just phase 4. What we have basically done is, for every item, we have divided its lifetime into several phases. What phase a particular item is in, we can easily keep track of, right? Because the item always starts, let's say, at phase 1, or it could have directly started at phase 2b, because let's say the immediate next item of I is greater than it, so then it will never enjoy a phase of expansion. So it starts somewhere here and then it only proceeds to a phase of a higher number. So that can happen at most like 3 or 4 times. And for every item, the number of phase change is 3 or 4. So the total number of phase changes is also bounded by, let's say, 3n, something like this. So if we have like an event for every phase change, we will have something like 3n events, right? So we have 3n events, 3n phase change events. Now, how do we intend to handle these phase change events? Well, we will process our queries not in the input order but in the sorted order of time. So we will process our queries in sorted order of t. And as we are processing our queries, we will also process our events one by one. So this seems still manageable, right? If we can count the number of occurrences, which we hopefully can, because when we know that an item is in a particular stage, it helps us count the number of occurrences, because let's say in stage 1, with every increasing time, we know that there will be one more occurrence. With stage 2, which is a stable state, we know that whatever the previous number of occurrences were where it ended stage 1, it will still have those many occurrences in phase 2. For phase 3, we know that after every 1 unit of time, one occurrence decreases, and in phase 4, we know that no occurrences are there, so we just delete it. So this seems more doable than our previous method of keeping track of what value was there at every ith moment. Now, can we actually count the number of items in a particular phase? And if so, how? So what are the difficulties that we can face? Right off the top of my mind, the first difficulty that I can think of is when we are at a border region, our phases kind of become more complicated, right? Because there might be some stable item entering here, but now it's like in an expansion phase when we look at it standing from here, right? Because let's say it's a stable item with both expansion and decay, so after the next time it would have been something like this, after then it would have been like this, and after this it would have been like this. But when you are starting your array from here, it seems like it's in an expansion phase, so that might lead to some confusion, like especially handling with the first endpoint, same with the second endpoint. So the first thing that I would like to do is break our query into two prefix queries. So in the first prefix query, we calculate till here, and the second prefix query, we calculate till here, and then we just subtract the two results to get whatever is there in this region. So now our problem reduces to taking the sum in a prefix. Now let's follow the confusion in which state an object in a bit more, because we still have one of the endpoints to deal with. Well, I claim that there will be only one item which is passing over this particular line. So when I say passing over, I mean that let's say it is in an expansion phase and it has kind of crossed this line. So it started from here and now it's expanding rightward. Or let's say there was a decay item, and the decay item, let's say, ended right about here, okay, at this point, and it was getting decayed from this side, which is also, again, there will only be at most one item which is overlapping with the end zone. I mean, we could have argued that that is also the case with the first zone, but it's easier for us to handle, like there are lesser number of cases if we divide our queries into prefix sums. Now, for the timing, let's forget about this corner case. We will deal with it later. How do we calculate the number of stuff that is there in each of the phases? That is our main problem. So instead of saying that there can be an expansion phase, there can be a decay plus expansion stable phase, there can be just a stable phase, there can be just a decay phase, and there can be a deleted phase. We will try to reduce the number of cases. So deleted phase isn't really a extra case, we are just not considering the number. So every time we get an event that okay, a particular item has hit the deleted phase and it is now getting deleted, then we just chuck it out. We don't really need to process it. Next, there are essentially three main things that we need to do. First is this stable phase where nothing changes. So we want to have some structure that can answer what is the total sum of items, or rather total sum of every item that is in a stable phase. So one structure which can answer sum of all items in stable phase. Okay, so I mean that let's say this was a item in stable phase, this was an item in stable phase, this was an item in stable phase, and let's say the value here was let's say the height was 3, the height was here 4, the height was here 5, and the spanning regions were also of length 3, 4, 5. Then we should be able to get 3 into 3 plus 4 into 4 plus 5 into 5 in hopefully the fastest amount of time that we can. Note that as we are processing again, we know exactly which item is in which phase, because we are making 3n events. So we are making 3n events where each event denotes a phase change. So this helps us keep track of what phase every item is in. So this was kind of the first thing that we need to do. For this corresponds to basically phase 2b, normal stable. We definitely need to have one for expansion. So for expansion, it is just, let's say there are some items I, j, k that are in the expansion phase. What is the total contribution made by ARR of I, ARR of j, ARR of k? We need to answer that again as fast as possible. This is basically expansion. And we need to have one for decay. That let's say our initial sizes of the array were something given. So let's say when the decay started, so when the decay started, we had, let's say, x I occurrences of ARR of I, and after every t time this xi becomes minus t. So this is what we answer. Now notice how phase 2a also gets handled using this expansion and decay, right? Because we don't necessarily make another event for phase 2a, we just add the decay event along with the expansion event. That effectively takes care of the phase 2a. So we essentially need to make three event types. One is when it starts the expansion phase, which is obviously immediately for most of the items. So we don't even need to do that. Second is when it starts the normal stable phase, and third when it starts the decay phase, and lastly when it gets deleted. Since the expansion phase is not really a concern, we can just take these three events: when it starts the decay phase, when it starts the stable normal phase, when it gets deleted. And processing these events will allow us to account for all the cases that we imagined. So let's get into a bit more what the exact formulas might be. So now let's try to figure out when, or rather how we can identify when the events will take place. So for a particular I, so let's say this is I, these are some smaller numbers, and this is the first greater element to the right, the first greater element to the left. Now initially at the ith position, this is in the expansion phase, right? So it will keep on expanding till it hits the next greater element. Now when it hits the next greater element, at that time we register our event 1. So event 1 is when expansion stops and stability begins. That means we have entered the stable phase, expansion has stopped, and we are not increasing our occurrences anymore. Now when will it start getting deleted? Like when will the decay phase start? That will happen when the previous greater element finally catches up to it. When this happens, we launch our event 2. So 2 means decay has started. Now note here that we are not really bothered with the stability thing here. Why? I mean, even when decay has started, it might happen that this event 2 happens before event 1. Even then we can have a stable phase, right? And this will be the stable phase 2a. This will be the stable phase 2b. Like here it's expanding and decaying at the same time, here nothing is happening. So since we don't care about the stable phase, it doesn't really bother us whether we are at a 2a or we are at a 2b. We are only bothered with whether it is in the expansion phase or not, whether it is in the decay phase or not. Now a time will come when the expansion is completely overtaken by the decay. That means the decay has happened till here. We don't know whether this expansion will stop at here because we are not bothered with it right now. We are bothered with the ith location for now. So when that time comes, then we will say that we have hit event 3, which is death. Like this ith element no longer has a contribution, so we check it out. Now let's say we are currently in the expansion phase, that is we have not hit event 1 yet. Okay, then the number of occurrences contributed by the expansion is T into ARR of I. So this is the total sum contributed by the expansion phase of I. Note that we don't have to deal with like min of t comma next greater of I, where we call this the next greater of I and this is the pref greater of I. We don't have to deal with this here because we know that when next greater of I happens, then we will be hitting event 1. So when we register event 1, we will take this ith element out of our expansion set. So how are we basically getting the value from the expansion set? Well, in our expansion set we have certain values arranged according to their indexes, and we say that from 0 to r, get me the sum of all the values. So I get the sum and I multiply it by t, right? So for all the i's that were inside this, we get the sum of all the ARR of i's and we multiply it by t. Now what happens when decay starts? So here's how we should look at it. For a particular element, we have, let's say, started expanding, or we have expanded till a point. So let's say these are the occurrences of a particular element. Now I'm talking about when event 2 hits. At that time it may be expanding, it might not be expanding, but it doesn't matter to us because we don't really need to know how many occurrences are there. We know that if for a particular I, if decay started at di and we are now at time t, then the amount of stuff that has decayed is t minus di into ARR of I. So again we will take the sum over all those i's which are in the decay set, and I less than r, right? Because we are querying for a prefix every time. Now again we don't need to worry about when this might become 0, then what will happen, what if the decay thing exceeds till how much our expansion has already happened. So for example, maybe one might think about what happens when we have deleted all of them and we are still continuing. Don't we need a max of say 0 comma t minus di minus something blah blah blah? Well, no. Again, why? Because we have already divided our phases with these events, and we know that when something like that happens, that is when all the positions are deleted, we know that we will be hit by event 3 for the position I. That means when we are hit with event 3, we throw out our item from the decay set as well. Now how can we calculate this efficiently? Well, we break down this formula into two parts, t into some ARR of I and minus di ARR of I. So this suggests that since we are taking this from I less than r, we can use a segment tree to just get this sum. We can use some other data structure to again get this sum. Now note here that both of the values are only dependent on I here and not the time. And when we finally hit a event of type 3, we just remove it from here, like from the segment tree or whatever set that we were using. So every time it's the same thing. When initially we are in the expansion set, when we hit a event 1, we delete it from the expansion set. When we hit a event 2, we know that now our decay is starting, so we insert the items in our decay set. And when we hit a event 3, we know that we need to remove our item from both the sets. So here I am using segment trees, or in particular I am using Fenwick trees here because segment trees are a bit too slow for the problem. So I'm using Fenwick trees to answer all these range sum queries, because effectively every time we are reducing it to a range sum, right? This is also a range sum, or rather a prefix sum. This is also, since we are storing di into ARR of I, this is some value v which is dependent on I, and then we are taking a sum over it for I less than r and some valid values. So we are again taking a prefix sum here. For the even the expansion set, we were just taking a prefix sum like this. So if we just use some Fenwick trees, we can easily achieve these values. Now the only thing that is bothering us yet is what happens at the limit of the query, that is at the end point. Because when we are starting from 0, we don't really need to think about this endpoint because everything kind of moves towards the right. But what about this endpoint? Well, I claim that we can find which item is currently dominating over this endpoint. That means which item has fully covered this endpoint right now. If we can find that item, we know that This is the last item that will be covering all of these. So we can just take the sum over everything that is here towards the right, and for this item we can treat it specially. Now how are we going to find what item is currently overriding the item at ARR of j, or rather ARR of r? Well, we know that something will override it only through a decay process, right? Now something can eliminate me if it is greater than me. So let's say this is r. So something to the left of r which is greater than me, in particular the previous greater element for r, is the one that will erase it next, right? Now let's say after some time this will happen. Now who will erase this value? Well, the previous greater for this previous greater r, so there must be some value here which is effectively pg of r, so previous greater of r. And let's say after some time the value becomes like this. Now who will erase this value? The previous greater for this value, right? So something even larger. So we are again taking pg of pg of pg of r. So this should remind you of climbing the parent pointers in a tree, and we kind of want to find the first ancestor which has index j, such that j minus r less than equal to t, but however the previous ancestor k minus r is greater than equal to t. That means the position at k has not yet reached r, but this value j, this has reached r and is dominating over r. So how do we find this first ancestor? Well, what I did was I built a sparse table for it, and I can find that first ancestor in log n time. Let's look at the code for this problem. First, I have a Fenwick tree structure here. It just answers some of the basic queries like get some, update bit. Well, why have I written these in such a weird way? ABCLR, ABCDval, when I am not actually using ABC values at all. Well, initially I had coded it with a segment tree, and then just to keep the update and get methods compatible, I have just changed the implementation and not the function parameter, so that I don't need to break code. And I have also refactored the class name. Now here, so what is this extravaganza? It is just saying that let's say I want to set my value to y and my previous value was x. So here I just calculated y minus x and added that in my bit. Now here I have given a brief summary of the stages and some of the formulas. But again, all these max, min, etc. are taken care of by our events. So here are the three types of events. Now here I calculate the previous greater and the next greater elements. Here I am forming the events. So to form the events, I need the use of next greater and previous greater for every particular I, and then I am sorting the events according to their time values. Now I have 4 Fenwick trees. One is for the expansion set, one is for stable set, one is for decay state, and one is for decay helper. So decay helper is effectively that di into ARR of I thing, and decay is just that ARR of I thing. We also are storing a Fenwick expansion, because note that even though there are no events corresponding to start of an expansion, that is just because at the start everything is in its expansion phase. But we still need to keep track of how much something has expanded, or rather what is the total value of the expansion, right? Now here I have built the sparse table using the pref greater values. We will get back to answer prefix a bit later. So here I take the input, I sort all the queries according to their time values, I generate all my graders, form event list, generate sparse table. Now I have reversed the event list here because of a personal preference, one might say. I like taking elements out from the back and then doing pop back instead of taking elements from the front using a pointer. So I destructure my query, and then as long as I have events that are to be processed within the time t, I process them one by one. So notice here I have taken from the back and then doing pop back. So that's why it's important to me that the events are sorted by time in a decreasing order. So since I had sorted in the increasing order, I have just reversed the list. So if I get an event of type 1, it means my expansion has stopped. That is why in the expansion tree, I update it to 0. That means it no longer contributes anything. And in the Fenwick table, Fenwick tree, I am updating it to ARR of I into E dot time. So E dot time means it corresponds to how much it has already expanded. So let's say it had expanded 4 times. So I'm just storing ARR of I into 4. That will just effectively allow us to take the sum of a range when we are actually figuring out the value for a prefix. When we get an event of type 2, I am updating in the decay function just ARR of I, and in the decay helper ARR of I into E time. That is again back here in the formula, that is this portion. Di is basically E dot time, that is when the event actually happened. And then when I am dying, so I just set it to 0 in the stable tree, set it to 0 in the helper tree, set it to 0 in the decay tree. And finally we calculate the cost for the range A to B, and then we set it to the corresponding actual query index, and then we output all the queries. Now how am I implementing this get answer prefix function? It's pretty simple. So first we find the element presiding over the last element using the sparse table. Then I update using my Fenwick expansion tree. So notice how I multiply into t plus 1 because that was the formula that we had derived. Next we add whatever was there in the stable tree as well in this particular range, and then we subtract from the cost whatever was there in the decay tree. So this is effectively sum of error of I into t minus Fenwick decay helper gives us sum of di into error of I. And finally, we have to subtract whatever was contributed extra by our last element, that is the element presiding over the index r, that is given by this formula. And it's not too difficult to derive. It's just looking at how the timestamps work when we are expanding over r. So that was it. Hope you liked the problem and the solution. That's it for today. Thank you.